In level 4, we will be setting up models for quadratic functions just like we did in level 3, but the extra step is that we're going to be solving optimization problems, where you might have to find a minimum or a maximum value by putting your function or your model into the calculator. In this example, it says a Norman window has the shape of a rectangle surmounted by a semicircle of diameter 2r, equal to the width of the rectangle. The perimeter of the window is 60 feet. In part A, we're asked to create a function in terms of r that represents the total area of the window. So keep in mind that our goal in the end is to write an area function. And we want our only variable in this function to be r. So let's think about how we would be writing the area of this figure. Starting off, it may seem like we have lots of variables. The rectangle has a length and a width, and the semicircle has a radius. So if I was to find the area of this figure, I would do length times width for the rectangle plus half the area of a circle. So a circle is pi r squared. I would do 1/2 pi r squared. Now, since my goal is to get all of my variables in terms of r, I just need to replace L and W with expressions that are in terms of r. So I go back to the information I was given in the beginning. We have a semicircle with diameter 2r, so they're telling us the diameter of this semicircle is 2r, which makes sense, it's 2 radii. So I can replace the width with 2r. The width of my rectangle could be 2r instead of w. So I've already replaced w with an expression in terms of 2r, or in terms of r. And then my next goal is to get the length to also be in terms of r. They told us that the perimeter of the window is 60 feet. So I'm going to use that information to set up an equation for the perimeter. An expression for the perimeter of this rectangle, I'll keep my width as 2r, but I would have 2r plus 2, I have two lengths, so 2l, plus half the circumference of a circle. And the circumference of a circle is 2 pi r, so it will be 1/2 of 2 pi r. And this would represent the perimeter of this figure, which is equal to 60 feet. Now my goal is to have an expression for L that's in terms of r, so I'm going to solve for L. And I can simplify this part a little bit. I get 2r plus 2l plus the 1/2 and the 2 would cancel. Pi r equals 60. And I want to subtract these two terms over to the other side. So I get 2l equals 60 minus 2r minus pi r. And my next step would be to divide both sides of the equation by 2. And we get L equals 60 divided by 2 is 30. Negative 2r divided by 2 would just be minus r. And then we get minus pi r over 2. So I have an expression for the length in terms of the radius. Now this L and this expression for w can be replaced in my area function, and I can find a function for the area that only has r's in it. So a of r is going to be, I replace L with 30 minus r minus pi r over 2. And then that's times the width, which I replace with 2r, and then plus the area of the semicircle, which is half the area of a circle, 1/2 pi r squared. And there's my function for the area of the circle. I could simplify it a little bit if I wanted. Maybe I'll at least distribute this 2r to these terms. And so we get a of r equals 60r minus 2r squared. And then we would get minus pi r squared. The 2 and the 1/2 would cancel. Then we add on that 1/2 pi r squared. And there is our function. And it's actually okay to just leave it in this form too. You can just plug it in your calculator just like that. Either is fine. It's not real important to simplify it because your calculator doesn't mind if you don't simplify, as long as you enter the equation correctly. So this should say part B. Now we have to do the level 4 part of this where we optimize the function. And so we're going to plug it in the calculator, and when you plug it in your calculator, go to y equals and use x's instead of r's, and play around with the window until you can see the graph. And it should look like an upside down parabola. For the window setting, for the x min and x max, I went from 0 to 20. Remember that the x values in this case represent the radius. And for the y min and y max, these represent the area, because that's what our function represents. I went from 0 to 300. But as long as you can see the whole parabola, you're in good shape. Then to find the dimensions of the window that will admit the most light, we need to find the maximum point on the parabola. And the maximum point is 8.4, 252. Now, remember that your x value is the radius and your y value is the area. So 252 is the maximum area, but this question isn't asking for the maximum area, it's asking for the dimensions of the window. So we would need to give its radius and also the length and width. So the radius would be 8.4. The width would be 2 times the radius, which would be 16.8. And the length, to find the length, we're going to go back to our expression for the length up here and plug in r. So the length of this function, down here, I'm running out of room, would be 30 minus 8.4 minus pi times 8.4 over 2. And that came out to about 8.4 as well. And these dimensions should all be in feet. And there you have it.